And we are recording. And so let me hand the floor over to group 13.
All right, well, hello. I'd like to thank you all for taking time out of your day to be here. We are group 13, and we're proud to present our design for a small scale modular tracking heliostat, the Hive Stat. So our group consists of myself, Akshay Ramakrishnan,
myself, Jake Anderer,
Joseph Miller.
Hey guys, I'm Charles Datko.
Hello, I'm Erica Joe.
I'm Kevin Diaz.
And I'm Dari Sampson.
The problem tasked to our group in this presentation is the design of a novel heliostat with a focus on a small reflecting surface for low cost and easy deployment and installation. A field of these heliostats would be used to reflect the sun's light to a collection tower, as in the picture on the left, which would use the heat produced by this light to power a generator, which would provide energy. Typical heliostat facilities currently implement large surface area heliostats in the picture on the right, which require robust ground mounting systems and high upfront costs. Our design hopes to remedy these problems and create an opportunity for a power plant using this heliostat to break into the field of green energy.
So our heliostat consists of 2 linear actuators with 300mm stroke extension, an Arduino controller mounted with industrial Velcro, a pressure-treated lumber pillar with a height of 0.45 meters, and a steel base mount that was purchased off the shelf, and 4 expansion bolts that are near the base mount flange, a dual axis hinge, and a hexagonal mirror. And the hexagonal mirror is assembled from 6 individual triangular mirrors. And as the heliostat is manipulated, the white clip at the ends of the linear actuators slide across the mirror frame, which acts as a railing system. And at the neutral position, where the mirror is positioned vertically, the module has a height of 0.8 meters. The idea of implementing a hexagonal reflective surface is similar to the Fresnel lens from NASA's James Webb Telescope, which also consists of hexagonal mirrors. And by utilizing this specific shape, the heliostats are able to be installed extremely close together, which optimizes the field use around the central receiving tower. The modules which surround the central receiving tower will approximate a paraboloid, and research has shown that the efficiency from transitioning to a more circular heliostat geometry rather than a rectangular one increases from 69% to 71%. And the reflective surface assembly are 6 individual triangular mirrors, which are supported by an ABS frame.
Our team, we're very passionate about nature and the environment. So not only do we strive to protect nature by composing our parts of sustainable materials, but we also aim to mimic the genius of nature. Today's natural world has spent billions of years evolving to its current form. So why shouldn't we implement its design into ours? For example, take the human opposable thumb. It's a saddle joint, which is a type of synovial joint in which there are opposing convex and concave shapes that allow for multi-directional movement. Okay, so go ahead and give me a thumbs up and rotate your opposable thumb multi-directionally on its saddle joint. This concept has been realized in the angle actuation method of our design. It's a saddle joint. Another inspiration from nature, hexagons. They've been found regularly throughout nature. Bees are known to build their nests in the form of connected hexagons with 120-degree angles. This is because hexagons are the most mechanically stable shape. They exert forces evenly on all joints, and because it is the most efficient way to fill a plane with equal sized units and leave no wasted space which, like Erica was saying, allows for maximum tessellation of reflective surfaces and no shading or wasted space. Actually, if you were to look closely at the eye of a fly, you would see a sphere composed of hexagons, because nature has determined that this is the shape that allows for the highest light intake. Our group was so inspired by this concept that we decided to call our design after beehives. That's why we're called the Hive Stat. So also inspired by the natural world is our ground mounting system. During the initial brainstorming stage of design concepts, one teammate presented the idea of mounting our heliostat via tree roots. That idea ended up surviving the down selection matrix and expansion bolts, which are much like tree roots mechanically, were implemented. They're similar to tree roots because they expand once established, allowing them to anchor a structure into the ground via force exerted parallel to that ground. Furthering this idea, we continue to focus on the tree concept as we design the pillar of our heliostat, copying a tree trunk, which is mounted via roots and lifts its light receptive leaves toward the sun. As I mentioned, sustainability is big to us. In order to protect nature, our team aimed to consider sustainability of materials used to make all parts at all stages. Those that could be are manufactured of ABS, which is recyclable, and those that couldn't be due to load constraints of the machine are made of aluminum, which is the next best option. Ultimately, we went so far with this concept because we really believe that nature is intelligent, and we as a team understand that its designs have evolved over billions of years to reach their current most optimized form, which is why it's worth mimicking and sustaining.
Yeah, as Dario was saying, we wanted to incorporate nature into our design in the simplest way as possible, because we know in further classes, someone is actually going to have to manufacture our design. So we really put an emphasis on the ease of assembly. We tried to have the most off-the-shelf parts as possible that fit the design. Of course, we have some parts that came special made, but those are specifically for our like hinge joints, things that need specific functions. Basically, our price is we reduce it as much as possible. Our budget of $100 was not exactly met, but I believe our total price ended up being around $320. But this price can probably be reduced with bulk buying. So that's something we're going to look forward in the future if manufacturing occurs. We have 5 total subsystems, and when put together with assembly, it's about 35 different steps that can be followed to assemble our heliostat. And optimized field placement, we believe we just have to set the ground that we're going to put it in before we put it. So in the desert, we may have to like treat the ground, maybe some concrete, but it needs a flat surface so the expansion bolts can actually hold and maintain structural integrity.
So the end goal of this design project was to create a heliostat that reflects light to a central receiver system, resulting in the generation of heat and subsequent conversion to electrical energy. With that in mind, the heliostat improvements were defined by the customer as a reduction in manufacturing costs as well as solar concentration ratios. So outlined below in this chart are the specific customer needs that we created that would facilitate the design of a more efficient heliostat in terms of size and cost to reflective output. So a couple key components factored in below include the geometric limitations of the 1 meter squared per modular heliostat, manufacturing costs being under $100 per meter squared, precise accuracy in tracking and optical performance, as well as simplicity of installment. We also included other needs that would produce a well-rounded design, including accounting for the operation location, as well as the longevity or lifetime of the heliostat. So to interpret this chart, we'll use ground mounting, for example, which is the green box. For the ground mounting subsystem, we felt that the most crucial areas where the arrows go were to consider the shading minimization, the price cap, the use of space, as well as part pricing. And so, for example, for this subsystem, these needs were chosen as it affects how the heliostats would be installed or arranged around the collection tower.
So the first subsystem we'll discuss is the reflective surface. And the assembly consists of 6 individual triangular mirrors, as mentioned before, which are supported by an ABS frame. The reason for going with ABS is it's relatively low cost, around $1.50 a pound, and because of its high machinability. So in order to combat UV degradation, which is a common issue that we found with ABS, the components that are ABS will be coated with primer and paint. And an alternative would be adding a chemical UV stabilizer, but since having a coating of paint would be a much easier application, we decided to go with that instead. One of our goals during the design process was reducing the number of fasteners. And because of that, we wanted the mirror to be mounted on the frame using an adhesive, and the adhesive that we chose was the Scotch Weld acrylic adhesive. And the frame and mirror would adhere to the mirror mount, and the mirror mount is injection molded ABS as well. And then the 1-inch pin would go through the mount that is connected to the mirror and the aluminum U-hinge, and that will be secured with an M6 screw. And by creating the hexagonal shape using individual mirrors, the triangles can be packed closer together during the transportation stage of the materials during assembly. And also it would reduce the amount of leftover material when cutting a square mirror stock. And in case of damage, the entire reflecting surface would not have to be replaced, only the individual triangular pieces, and that piece would be removed and replaced. The 1-inch pin would be subjected to 71 newtons of force due to the weight of the mirror, and an additional 14.8 newtons of force was added due to wind loads. And we calculated that with 40 miles per hour winds in case of like a worst case scenario. And the shear stress experienced by that rod is around 170 kilopascals, which is well under the 38.3 megapascal shear yield strength. And that was approximated from the tensile yield strength multiplied by a constant from the von Mises criterion.
This slide considers the reflecting surface subsystem for 2 of the customer needs we identified in the map shown 2 slides ago. And the 2 of those are the thermal input power required for the generator and the solar concentration ratio of the collector on the tower. The thermal input power assumes a solar irradiance of 1,000 watts per meter squared and uses that to find how much wattage a single heliostat module of ours would send to the collection tower, which is about 300 watts. And the generator of this system is 1 megawatts, which would mean that a little over 3,000 heliostats would be needed to reach that 1 megawatt need. And for the solar concentration ratio, the formula presented on the slide here is unfortunately out of date, but the correct one is it's a 1,000 suns concentration ratio required for the customer need. And to reach that with the 3,000 heliostats identified, the minimum ratio of a single heliostat module area to the collector area is 0.3. This could be increased, but doing so would also increase the frequency of adjustments needed to the angle of the heliostat. A larger collector area would allow the reflected light to drift further in between adjustments while still staying inside the collector area.
So the mirrors were originally supported on the edge of all 3 sides to increase rigidity of the structure and to allow the mirrors to be connected easily together. However, we conducted a deflection analysis to see if the mirrors required any additional support. So the first equation shown on this slide represents the closed form solution of the plate with uniform lateral loads, and D represents the flexural rigidity of the plate. So solving this equation shows that the maximum deflection is located at the orthocenter, and it has a max deflection of around 7.5 millimeters. So to decrease that magnitude of deflection, an additional strip of ABS was installed near the orthocenter of the triangle. And that is the reason why there is like a small hexagon shape within the frame of the mirror surface. So the next analysis we conducted was to determine the proper adhesive to use for the mirror structure. As we know, it is used in the desert, so it must withstand some high temperatures. So the first equation that is seen on the slide represents the energy balance equation that we wrote out. And the first term is the radiant energy absorbed from the sun. The second term is the radiation from the sky. And the third is the convection of air. And the right is equal to the mass times specific heat times the change in temperature over time. But assuming steady state, the right side goes to 0, and we solve this equation for temperature. And the results showed that the adhesive that would be chosen in our final design must withstand at least 285 degrees Celsius. Thankfully, there is such an adhesive to withstand such high temperatures, and we found that the Scotch Weld 8610 adhesive withstands up to 350 degrees Celsius and requires minimal preparation during installation.
So due to budgeting, we made our pillar made out of wood rather than some metallic material, strictly just to lower the price. And when we made this change, we wanted to ensure that the pillar would hold structural integrity due to any outside forces that may arise. So the first analysis that we conducted on the structure determined whether or not it would break due to, say, a wind force acting. For this analysis, we used the worst case scenario, a max wind force velocity acting perpendicular to the pillar. We also used the dynamic pressure to determine this. Once we found the force acting on the weakest point of the pillar, it was determined that, in fact, the wooden pillar would be able to withstand major wind force in unideal conditions, and that we could go with this design. The next analysis that we conducted due to structure was determining whether or not the hinge would actually be able to hold up the reflective surface. From this analysis, we used bending stress along with each component's respective weights. We used the weight of the mirror and mirror body as long as the weight of the hinge, pole, and shaft combined. So from this analysis, it was determined that the hinge would be able to withstand the force of the reflective surface while being connected to the wooden pillar.
So now to talk about controls. To control linear actuators, an Arduino Uno with Wi-Fi will be externally mounted to each heliostat in an OTS box. And then a separate dual channel DC motor controller will be wired to the Arduino linear actuator to boost the Arduino's amperage and allow it to power linear actuators, because alone the Arduino would not be able to move those actuators. Then talking about the linear actuators, we selected these linear actuators because they're a commonly used OTS part from Amazon and are appropriate for aiming the heliostat mirrors at the concentrating tower in an outdoor and desert environment. They are not only geared powerful enough, but in unison with the saddle joint, allow for effective 2-axis tracking of the sun. And relative to the sun, the actuators are very fast and have no problem keeping up with it, especially with the spec'd out battery that allows for 9 hours of low load actuation with a 20% buffer capacity. So ideally, they'd be changed daily.
For our actuation, as previously mentioned, we use 2 linear actuators, and on both ends, where the bottom connects to the wooden pillar and the top connects to the underside of the reflecting surface, we have 2 axis hinges, which allow the linear actuators to both move independently from one another and allow them to rotate the full range of motion of the reflecting surface as it tracks the sun throughout the day. And for our control subsystem, we used a pre-programmed schema where astronomical data tells us where exactly the sun is in the sky throughout the year for the latitude and longitude of our location. And so the heliostat is able to track the sun automatically using the pre-programmed path in the Arduino. And as mentioned on the slide here, allowing the actuators to move independently from one another reduces risk of damage to the mirror in case of malfunction. One of our previous designs did not have this capability for the actuators. And so if one extended and the other was stuck or unable to move for some reason, then it would put immense pressure on the mirror and might shatter it. As mentioned, the heliostats are to be installed near Las Vegas, Nevada, which is about 36.17 degrees north. And Earth's tilt of 23.5 degrees changes the sun's position in the sky throughout the year. It gives a range of 59.67 degrees to 12.67 degrees from the vertical in the southern part of the sky. In addition, the sun also moves 180 degrees from east to west, but the majority of energy is available when the sun is high in the sky, making angles near the horizon less desirable to reach. And the assumption here is that the heliostat field is north-south aligned with the tower in the south, and that would minimize the sun-tower angle, as the sun is always going to be in the southern half of the sky. So putting the target to which it needs to reflect the sun's light also in the southern half minimizes that angle. We also assume that the heliostats would be located between 50 and 100 meters from the tower, which would, on the low end for 50 meters, it would mean that the heliostats would not have to reach as high of an angle to reach the top of the tower, which we also assumed the collector would be at maximum 100 meters from the ground. At the 100 meters out from the tower is about the distance where we would need to consider the optical effects, where the light would spread out slightly over that distance and the effectiveness of the heliostats would decrease. And so what we determined is the angles there presented are the angles of the 100 meter tall tower collection from vertical. And the heliostats work by reflecting light, so the law of reflection is used where the angle of incidence equals the angle of reflection. Therefore, unlike a solar panel, which would need to point directly at the sun to get the most out of the light, a heliostat pointing directly at the sun would just reflect the light right back at the sun. So instead, it needs to point directly in between where the light is coming from and where the light needs to go, which bisects the angle between the sun and the tower. And so using that relationship, we can find the maximum angle the heliostat would need to move in the north-south direction to get the sun's light reflected to the correct location at any time of the year. When the sun is highest in the sky, there needs to be, the heliostat needs to be up to 19.62 degrees from vertical. And then when the sun is lowest in the sky, it needs to be 52.34 degrees from the vertical, which gives us our range of actuation in the north-south direction for the heliostat. And then in the east-west, as I mentioned, it's 90 degrees in either direction. So the minimum and maximum angle it needs to rotate in the east-west is identical. And the north-south angle actuation is achieved by the higher mounted actuator, which is there because the heliostat would only ever need to face the southern part of the sky. For the east-west actuator, it's mounted a little lower, which would allow it to get a more even and equal actuation in that direction. They're attached by a plastic support, or attached to the plastic support by clips screwed into the connector, which Erica mentioned previously. They would slide along the rail to give that little extra range of motion that the linear actuator alone would not be able to provide.
Lastly, we have the ground mounting system, which is like the tree roots of the heliostat. So we have a wooden pillar which is fastened to a metal base and bolted down by 4 expansion bolts. Arranging these expansion bolts in this rectangular form is, according to research, the most mechanically stable method of arrangement. The anchor bolts are approximately 4 inches long, or 0.13 meters, and they are made of steel. They can be mounted directly into the desert ground because of the stiffness of the sand. No concrete is needed. As they are bolted into the ground, their expansion ring ruptures open and it locks the bolts into the ground. Another common application for these bolts in sand is with windmills.
An analysis here was conducted. First on the slide, it's presented the force between the bolts and the metal flange through which they're mounted. And based on the previously mentioned 40-mile-per-hour wind gust, we calculated the maximum stress that would be produced, which is 14.57 pascals, which is a very small number. So the risk of failure in that mode is very low. Another analysis that we conducted, which is not presented on the slide here, was we also did a soil analysis. The location near Las Vegas, we found it's mostly loam soil, more than 5 centimeters below the surface. So the majority of the length of the bolts would be interfacing with that soil type. We found that that type of soil experiences serious compressibility effects at around 300 kilopascals of pressure. For this, we assumed a 50-mile-per-hour gust because we realized that it would, if the ground mounting were to fail, it would be in the interface with the soil. So we wanted to consider the absolute worst case scenario to see how the bolts would fare in holding the entire assembly into the ground. The heliostat we assumed was in its neutral position, which it would go to in the case of a high wind gust to reduce the chance of damage. We found the area of the surface area presented to the wind was about 0.11 square meters, using the formula of air density times surface area times wind velocity squared. This gives us the force that the wind produces on the entire heliostat assembly, which was found to be 67.5 newtons. The centroid of the side profile was then found to be about 0.4 meters off the ground. And so that produces a moment about the base where the bolts are located of 26.7 Newton meters. From here, 2 analyses were conducted, one on the bolts pressed into the soil, which would produce forces from the side, and then one on the bottom of the pillar and the flange, which would compress the soil from the top. For the bolt, the length in the soil is about 10.5 centimeters, and they have an average diameter of 1.3 centimeters. With 4 bolts, this produced a maximum pressure on the soil of around 46 kilopascals when considering a crushing mode of failure. And this is far below the 300 kilopascals that would compress the soil enough that it would potentially move or wobble, which would destabilize the heliostat. For the second analysis, both the wind force and the force caused by the weight of the assembly were considered when calculating the compression of the soil. The mass of the heliostat is around 15 kilograms, and the area of the bottom surface of the pillar is 0.16 square meters, and this produces a compressive stress of 9 kilopascals. Using the force from the wind and the moment about the base, it produces a compressive stress of 55.5 kilopascals for a total of 64.5, which is also far below the 300 necessary to compress the soil. Considering the environment of the installation site, it receives an average of 5 inches or 12.7 centimeters of rainfall per year. The accumulation of water weakening the soil is not as much of a concern. However, if the installation site is prone to situations involving simultaneous heavy rainfall and high winds, the soil may be infiltrated by water to a degree where it would be compressed, tilting the heliostat and ruining its ability to effectively track the sun and reflect its light to the central collection tower.
So as you can see, the OTS parts of the manufacturing takes up the largest portion of the cost. But we estimate that once due to commercial and bulk quantities when purchasing, it would go down to a lower amount. And then the energy consumption amount is incorrect, but still due to the 24 hours of the Arduino and the linear actuators running, it comes out to 23 cents, which is still pretty insignificant. And then with the assembly labor, we estimate that would take 1 hour and 4 minutes with that cost. And then for manufacturing labor, it will be 1 hour and 10 minutes. And why this design? Well, first off, it's budget friendly. Again, with the materials we have, we estimate that would go down. And then we used cheaper materials whenever we could with the pressure treated lumber and other in the mirroring surface. And then we also cut down on size as much as possible.
Another standout feature of their design is the unique and modern look it boasts. The Hive Stat features a hexagonal reflective surface designed after beehive to promote optimal tessellation between the modules. Additionally, the ground mounting subsystem is accomplished by expansion bolts, which are inspired by the mechanics of tree roots, which anchor into the ground by expanding once established. Furthermore, the structural body is a wooden pillar, and that's designed after a tree trunk, which maintains a minimal footprint, causing no shading of the surfaces and allows the opportunity for optimal reflective surface solar radiation. So overall, our group believes in the simplicity found in nature and therefore use biomimicry to create a unique and modern design.
The Hive Stat also has a seamless assembly method. It takes under 40 simple steps.
And our design also capitalizes on innovation by introducing a relatively uncommon shape in practice for reflective surfaces. Also, the linearly actuated heliostats that are currently in use require large cross-sectional beams supported by individual hinges, while our design implements a universal hinge, which reduces the amount of parts necessary to facilitate that dual axis motion.
And lastly, our design utilizes these linear actuators, which negate any sort of delay that may occur due to an error with sun data. These linear actuators experience no optical feedback, which allow the heliostat to track the sun during all working hours.
So overall, the Hive Stat design addresses all the given customer needs and can be competitive with similar products in the market. It is budget friendly and features a unique design not seen among other competitors. Furthermore, the design allows for seamless assembly and is innovative in its use of linear actuators to accomplish multiple axes of rotation. Finally, the design is fully autonomous in its ability to track the sun throughout the day. So with that being said, we hope you enjoyed our design presentation and want to thank our corporate sponsors for being here, as well as faculty. And with that, we'd like to open up if you all have any questions. Thank you.
Hi, Dan Plawecki. I've got a couple of questions for you. The first one is with heliostats. One of the unfortunate problems is they tend to be bird killers. And there could be some relatively large sized birds that could be impacted. And I'm wondering if you did any calculus in your stress work that you did to consider the potential impact of a bird strike on your structure.
With this, it would be most related to the soil analysis that I did. That would probably be the earliest point of failure in the case of a bird strike, like you mentioned. And that gave us a For a 67.5 Newton force on the heliostat, it gave us about a 5 factor of safety, which would mean about 300 Newtons of force would be enough to potentially compress the soil and uproot the heliostat. We didn't do any specific analyses on how much force a bird strike would do, but depending on the size, it potentially could damage the heliostat structure.
Yeah, so that raised another issue is repairability. So if you did incur damage, you'd have to either replace the whole assembly or replace elements or components of the assembly that failed, like the ABS frame. And it didn't see any provisions for repairability. Your mirrors are bonded to the ABS frame. So if you had any mirror damage, you'd have to remove and replace the whole ABS frame and mirror assembly. Just wondering if you gave it any thoughts to long-term life cycle cost of maintaining the assembly.
So looking at that, we tried to avoid fasteners for for replacing the mirrors, just as a cost measure. But ideally, let's say a bird strikes I guess not ideally, but let's say a bird strikes the mirror surface and breaks one of the mirrors. Ideally, it would only break one of the 6 mirrors. So then we would try to reduce downtime, we would disconnect the 6 mirror assembly from the saddle joint, set that aside for repair, and then put a new one in. And then since it's only one of the mirrors that got damaged, we could just unbond the broken one or whatever's remaining of it and replace it with another one, and kind of have a rolling inventory of parts like that for repair.
Okay, good enough. Could you go to the chart that you had on the reflective surface that showed the pin installation? Your 1-inch pin.
You guys should be able to share again. Sorry, you gave me host privileges and probably lost the ability to share. It should be up again.
And it should be, I believe, it's slide 6, maybe.
Yeah, it's around there. We're not seeing it yet.
You on it, Kevin?
No, we're not seeing a slide deck.
There it comes.
There it is.
Okay, so keep going. Yeah, right there. So you got your ABS pin that is interfacing with the web assembly, the ABS web assembly. I know you did know that right there, the lattice assembly further up. Where that pin interfaces, I know you did some analysis on the pin itself, but how do you plan on attaching that pin to the ABS? Is it going to be an ABS welded joint? Is it going to be bolted? What is the plan for that attachment? Because it seems like that would be the stress riser. That would be, if that structure were to fail, it would probably fail at that interface. And I'm curious if you calculated what type of margin you would have at that point.
For the ABS pin itself,
The interface,
Right.
however, whatever your attachment method is. Are you bonding it? Are you mechanically going to secure it with hardware? Are you going to plastic weld it? So you got an ABS pin and you got an ABS lattice frame.
right.
So how are you going to attach it?
I believe, correct me if I'm wrong, anyone, but I believe the pin is only used to attach that ABS, the wide ABS mirror mount to the hinge. The mirror mount would be attached to the frame.
Okay.
Bond, or
Okay.
the adhesive, just like the mirrors.
Right.
Okay, so the pin itself would be holding in the mount, the ABS mirror mount, and would not be connected to the lattice structure at all.
No.
Got it. Okay.
Although you did mention repairability earlier, that would potentially introduce, if the pin were to break, then you'd have to unbond the mirror mount from the lattice.
Right.
That's why we focused on the pin because we knew if something like that were to happen, that would be the hardest thing to replace.
Okay,
Right.
good. Could you go to the slide where you talked about the temperature calculus you did on the adhesive?
Here we are.
So 285 degrees C, that's pretty hot.
It is.
Could ABS withstand those temperatures? I thought ABS would become very soft as you approach 285 degrees C.
About 200.
Yeah, what is even driving? I mean, I'm not like necessarily following the temperature analysis here, but we're reflecting most of the sun's energy, right? So where is the energy to heat anything up to almost 300 degrees C coming from?
I believe, who did this analysis on this slide?
It was measured from the absorptivity from like a max temperature, but the temperature was systematically shifted upwards just for like a failure safe. So the actual temperature experience would be slightly lower than 285.
Oh, you mean like this is if the adhesive were in direct sunlight?
Right.
Yeah.
Worst case scenario.
Okay. So the adhesive under the mirror would be at a significantly lower temperature because most of the light.
I mean, the whole thing is going to be at a
Would be
significantly
reflected.
lower
Right.
temperature. I don't think anything in your structure could possibly get to near 300 degrees Celsius.
Right.
Like if you're building a solar oven, right, and intentionally trying to capture and retain the sun's heat, like you'd have trouble achieving this temperature, I think.
Yeah, I believe a more realistic analysis could have been more appropriate here, but this was the worst case scenario is the analysis we conducted on this slide.
Your worst case has still got to be like feasible, because I mean something like this. There were a couple of points where I really raised my eyebrows here, and this was one of them. Another one was I think you said that you intend to power your system with batteries.
Yes.
And that you intend to change those batteries once a day.
Right. That would be more of like a as a preventative measure, but let's head over to that slide. So
Well, first of all, I'm pretty sure your customer said they were going to provide you power, right?
right.
But even if they don't, well, I mean, like who's going to go? I mean, you need an array of, I think you said like 2,000 of these mirrors, right? Who's going to change 2,000 batteries a day?
So that is a good point. I spec'd it out more as like as an option. Ideally, it would be provided customer power. I mean, given that the solar farm itself generates electricity, that would be more appropriate than using batteries.
Yeah, I think it would be. And another place where I raised my eyebrows, you said you're putting expansion bolts into soil.
Correct.
And I mean, I'm not a geo guy, but I can't possibly believe that 4 expansion bolts, which look like they're on the order of, 2, I think you said like 10 centimeters, so like 4 inches long. I can't possibly believe that those are going to hold things in the soil, particularly when you get a wind load that is going to bend this thing kind of in the direction of that arrow at the top, the wooden pillar topper, right? So it's going to bend these things on the weak axis. Like, how are you going to develop a force couple that's going to withstand that moment with expansion bolts? Yeah, exactly. With expansion bolts driven into the soil. Again, I'm not a geo guy,
right,
but I can't believe that's even remotely feasible.
Even if it was concrete, it'd be questionable.
Yeah.
Right. Okay.
Yeah,
And I'd also say if you were in concrete, I would suggest that a bracket would be much more structurally efficient if your bolts were sort of uniformly spaced around the outside rather than giving yourself a very strong axis like you've got here and then also a very weak axis.
Right. Right.
You can say what you're going to say.
Oh, right. I could definitely see how a different bracket shape to eliminate the weak axis more of a square instead of a rectangle would help. This was selected more as like an OTS solution. I'm sure that there's better solutions out there for in terms of like OTS, maybe having 1 bolt per side or maybe even longer bolts.
Yeah. Well, even if it's not off the shelf, how much does your system cost?
So looking at what we spec'd out for retail pricing, we have 373. But I suspect that contacting the linear actuator vendors, because that's where a lot of our cost is, with each linear actuator being about $30 to $35. So multiply that by 2, that's $70 just for linear actuators. If we contact a seller and work out a commercial deal, I'm sure the price will come down.
All right, so the price is going to come down from 373. Say it's 300. You're 3 times the cost of what your customer wants to pay for these, right? So why are you worried about an off-the-shelf bracket?
Yeah, that's a good point. That would be a good place to dedicate a little more money.
Our original thought for using
look for the
bracket
low-hanging fruit to save money on here, because I mean, as is, if I'm the customer and you tell me I've got to pay 3 times what I think is reasonable for your system, I'm walking out the door. There's no point in me sitting through a presentation like this.
Okay.
Okay.
So one more question. If you go to your controls slide.
Yeah, sure. Ooh. This one?
Right there, yeah, that there. So this box is going to be exposed to solar load and convective thermal load. Did you do any measurements to see if your electronics were going to survive that environment?
Yes. So on the Arduino website, the Arduinos were spec'd out to be able to withstand up to about 180 degrees to 170 degrees Fahrenheit in terms of temperature. And if you think about, say, a car in a parking lot that's under the sun, reaches about 130 degrees Fahrenheit, 140 degrees Fahrenheit. So I think that as well with the vent holes, I don't think the temperature is of concern for the Arduino or the motor controller, which is rated for like infinite operation at 3 amps. So I thought that's fine.
In addition, we tried to mount the Arduino box. You can see there as high as we could on a pole, which would mean for the majority of the day, it would be completely shaded by the reflecting surface directly above it. And only when the sun is very low in the sky would it ever receive any direct sunlight.
Okay, so the other question on that box is you appear to have cooling slots in there. And one of the problems is with insect infestation that would cause problems with your electronics.
Right.
So that's something you might want to take into consideration.
Okay. Right. It's not pictured in our models, but for wiring towards to the linear actuators, we would use electrical conduit to cover the wires, not only from insects or rats, for example, but also from the sun and dust. That would be more of a concern for the sensitive electronics, the smaller stuff, but the linear actuators are rated for outdoor use. The IP54 weatherproof rating.
Okay.
Right. So I mean, as long as it's not underwater, which is not likely to happen in a desert, it should be fine when it comes to weatherproofing.
Okay, that's all the questions I had. Very good, thanks.
All right.
Okay, so we've actually eaten into most of the break, which is supposed to run until 2:45. So that's probably a good place to stop. I just want to make one comment before we stop, which is to say that I've taught this class, probably 8 times, 9 times now since I started. And I always wonder whether students are really listening. And I appreciate right in the beginning, you guys were talking about how you go through, or how you went through a decision matrix, and tree roots was in your decision matrix. And that ended up giving you the inspiration to do that ground anchor solution, which I think, as Tom pointed out, might have some weaknesses associated with it. But what I really appreciate, yeah, there we go. Yeah, what I really appreciate is that you guys did not throw out the idea of tree roots the moment that somebody conceived of it, right? Students do that a lot, right? It's, oh, how is this thing going to possibly grow tree roots? Let's throw that out, right? You actually kept it in your down selection matrix and then used it to inspire, something else that potentially is more viable than having the system grow tree roots. So I think that's a really good example of why, unless a concept is truly impossible, which I have a whole lecture on, unless it's truly impossible, why you don't throw it out early on in the process, because it can inspire other ideas that are more feasible. So anyway, I appreciate that you guys kept it in there and that you actually mentioned it. It lets me know that you're listening, so I appreciate that. On that note, we'll wrap up and give everybody at least a 5-minute break. So stop recording.